So if there's an infinity in the limits of integration, maybe something like this, the integral from, I don't know, maybe some a to some infinity of f of x, we can't use the fundamental theorem of calculus because infinity is not a number. But all we're going to do is say that this actually works because the Riemann integral is a continuous operator. But anyway, that's not calculus. That's further than calculus. We can do this as setting it up as a limit from a to b as b goes to infinity. So if we can't use, this is not a real number, but this is a real number. And it turns out, since f is continuous and the integral is a continuous operator, that we can use the fundamental theorem on this. And then as b goes off to infinity, we do get convergence of this limit. And that is indeed equal. That's all we're going to do. It's nothing new. Let's see how it looks when we put it together. Example 1. I'm going to get a shirt. I'm going to get a calculus shirt that says, it's really nothing new. There's nothing new in this section. Evaluate. Part A, the integral from 1 to infinity of the natural log of x dx. So I hope you should have an expectation of whether this integral is finite or infinite. This is what natural log looks like. So the area under the curve, well, this function just keeps going forever and ever. It slows down, but it can get as high as it wants. So specifically this blue area, do you agree that this blue area is bigger than this green rectangle? And this green rectangle goes off to infinity? I hope so. The blue area will be bigger than the area of this green rectangle. Well, maybe this rectangle has a height 1, but it has infinite length. So this rectangle is infinitely big, has infinitely much area. So the blue, which is bigger than something infinitely big, should also be infinitely big. Spoiler alert, that's a comparison theorem that we talk about in the 7th video of this section. If something's bigger than infinity, it's infinite. All right, not super profound, but useful. But let's show it using the techniques of this section. This is going to be the limit. You can use whatever letter you want. B to infinity of 1 to b of ln of x dx. Now we can evaluate this integral using integration by parts. You don't need the formula for this. You can use integration by parts. And if you use integration by parts, remember that we can let u be ln of x and dv be dx. Integration by parts will get you the answer. And you're going to get that this answer, I wrote it down to save us some time, is x times the natural log of x minus x, I think. Where'd it go? Minus x, great. And that's getting evaluated from 1 to b. So that's the limit as b goes to infinity of b times the natural log of b minus b minus what happens when we plug in 1. 1 times the natural log of 1 minus 1. Okay, that looks kind of weird. The natural log of 1 is 0. Doesn't really matter though, because what is this limit? Natural log is going off to infinity. B is going off into infinity. We're getting it. Oh. What is this limit? We've got infinity minus infinity. What is that? Is it 0? Is it infinity? Is it minus infinity? I don't know. Infinity minus infinity. That's an indeterminate form. We need L'Hopital's rule. Oh, man. Okay, so let's look at this. Actually, there's even a nicer way of doing this so we don't need L'Hopital's rule. Watch this. Let's save ourselves a little bit of effort. This is the limit as b goes to infinity of, let's factor out a b. We get ln of b minus 1. And then again, this is 0, and that becomes a plus 1. So this way looks a lot nicer than infinity minus infinity. Because what is this form? This is going off to infinity, and this is going off to infinity. What's positive infinity? An infinitely big number times an infinitely big number is still an infinitely big number. Great. But you cannot conclude that this is positive infinity. This is an indeterminate form. But if you factor out a b, now we have infinity times infinity. And yeah, that makes sense. That's also an infinitely big number. So that is, this limit is infinity. We say that this limit diverges. We say the integral diverges. And what that means is infinitely big or small area. Let's not say big or small. That's kind of ambiguous. Infinitely big. Maybe it's negative. Right? Infinitely big positive or infinitely big negative. That's what diverge means. Converge means it goes to a number. The limit is a number. So this blue area, infinitely big. This blue area goes off to infinity as well. That's going to be the next problem that we're doing, right? This area goes off to infinity because there's an asymptote. This function never hits 0, so there is infinitely much length for this area. But it turns out that this whole blue area, this infinitely long blue area, is actually finite. Let's see how. Let's see why. Let's do a little digging. Part B. The integral from 1 to infinity of 1 over x cubed. Was that the function? Yeah, x cubed dx. Well, okay, we can't use a fundamental theorem on infinity, but we can write this as a limit. Let's use a different letter. Let's change things up. Use a. You can use any letter you want. Integral from 1 to a of 1 over x cubed dx. We can use the power rule to find the antiderivative. This is just x to the negative 3. To add an exponent is x to the negative 2. Divide by that exponent, divide by negative 2, looks like this. And again, you could go off to the side and do it in this notation. It'd be a little clearer. That's an A, not a 9. Writing your A's like A's would also make things a little clearer. And now we just use a fundamental theorem of calculus. That's going to give us a negative 1 over 2 times a squared minus a negative is plus a positive. We get this as our integral, which is fine. Whew, I panicked there for a second. It's fine. Now, what is this limit? As a gets incredibly large, what is this limit? Well, as a gets incredibly big, we have 1 divided by double an incredibly big number. It goes off to 0. As a goes to infinity, this guy goes to 0. What are we left with? 1/2. That whole infinitely long blue area is just equal to 1/2 units squared. Okay. The power of limits, my friends. We'd write units squared if we were asked about area. This is just asking about an integral, which can represent area. The integral is just a number with, it doesn't necessarily have any sort of units. And yeah, that's it. That's where we go. That's how you can do these infinite integrals. In the next video, we have a cool application. This happens all the time in probability and some statistics. So good luck. Bye-bye. Have fun.